signals and digital circuits. Okay, so as I said, the input is only going to be either zeros or ones or highs and lows. So let's say this is time, this is some input or output. And then this is only going to be either high, which is 1, or low, which is 0. Okay, so we look at two types of digital circuits. One is those which use combinational logic. Okay, examples would be, you probably heard of this, OR gate, NOR gate, XOR gate, and so on. And these are what they call, what we would say is that the outputs are function of instantaneous inputs. We've provided the circuit input of zeros or ones, the output will immediately change based on those inputs. The other types of circuits we'll look at are sequential logic circuits. Now, these actually keep track of history. So the output depends on history of inputs. Okay, so it's not just the current value, but what has gone into the circuit in the past. So examples of this would be, as I said, would be gates, AND gate, OR gate, and so on. And an example of this would be flip-flops. Okay, and we'll talk about flip-flops a little bit later. Okay, now before we actually dive into these circuits, this is sort of a refresher on how do you represent numbers with zeros and ones. And then you can do the same thing for alphabets, characters, and so on. So digital representation. So an example is, let's say that's the number 523, which is what in the system we are used to, which is the decimal system. So in decimal system, you can have a number 0 all the way through 9. And those are 10 digits, right? 0, 1, 2, so on till 9, so 10 digits. If you want to write this down as a combination of multiples of 10, then you will write it as 50 times 10 raised to 2 plus, let me write it this way, 500 plus 20 plus 3. So I've broken down to ones, tens, and hundreds, and this can be further broken down as 5 times square plus 2 times 10 raised to 1 plus 3 times 10 raised to 0. Okay, so this is how you would factor this down into multiples of 10. And the reason why you want multiples of 10, then what you can do is, if you know that if you have a computer which stores the ones, tens, and hundreds digit, all you need to do is say 5, 2, and 3, right? And then 5, 2, 3 gives you the information that it is, well, in this case, 523 is 523. There's nothing to be interpreted here. but you just have to save 5, 2, and 3. And then there's this whole thing which goes behind it. So this is probably very obvious and it's very clear, but then let's try to see how you could potentially represent a number in zeros and ones, right? Because that's where we want to go, and that's how the computers interpret numbers. So here's an example of a number 100. Okay, now 100, well, 100 in decimal units is 100, like the number 100. But this number is not in decimal units. It's basically in binary units, which means that the highest number can only be 1, zeros or ones. In fact, if you saw 10, base 10, you didn't see a number greater than 9, right? Similarly, there is another system called hexadecimal, 16, where you'll see the highest number is 15, but not any greater than 15. So the question is, how do you break down 100? What does 100 really mean in decimal systems? So you can actually convert from one system to another. So the way you'll do this is take 1, take 0, and 0. And then all you do is you do something very similar to this. You see that I multiplied this with 10 raised to 0, 10 raised to 1, 10 square. Similarly, I'll multiply this 2 raised to 0, 2 raised to 1, and 2 raised to 2. Okay, this is very similar to. Okay, so that's sort of the first example gave an intuition how to break it down. We're using the intuition for a binary representation. And what we can now do is we can actually convert this to 2 square is 4. It doesn't really matter what's here, it's 0. And then this is 0. So this number is 4. Right? Yeah, it should be 4 in base 10. So the number 4 in base 10 is 100 in base 2. So this is just saying that you can convert from one system to another. You could do a similar process to convert from the binary system. There's a octal system, base 8. There's a hexadecimal system, base 16, and so on. Now, in this example, 100, this is known as the first digit is known as the most significant bit, MSB, and 0, the last digit is the least significant bit. So that gets to what is a bit. Bit can be 0 or 1. Okay, so it's just a simple logic which tells you the number is 0 or 1. There's something called byte, which is made up of 8 bits. Okay, so what does this really mean? The way I can relate this to what you might have heard or seen is when you buy a hard drive, okay, let's say that you bought a 2 terabyte hard drive. 2 terabyte. What this means is this is 2 raised to 10 raised to 3 bytes, 2 10 raised to 3 times 8 bits. And so this will be 16 times 1000. Wait, something is wrong. Tera is not this. Tera is 12, my bad. Can't be that close. So 1.6 10 raised to 13 bits. So your hard drive 2 terabyte right now is like on the higher end of the spectrum. If you buy that drive and you fill it up with your movies or whatever you want, you'll be basically storing 1.6 times 10 raised to 3 bits. Okay, if you use half of that, you'll be storing half of those many bits. That's, by the way, a big number. 10 raised to 13 is gigantic, right? So as I said, this is just one of the many systems. You could also have base 8 system, known as octal, base 16. Hexadecimal. Okay, it's not quite used in a computer, but you will see that many times they will write, if you look at, let's say, encoders, you'll see that they will actually say that this is how you communicate. They'll tell you the values in terms of hexadecimal systems. So you better be ready to convert this to the right number. So it spits out, your output comes as hexadecimal, and then you need to take the hexadecimal, convert it to a decimal system, and then use it for your purposes. So you should just be aware that it's been done. And for that matter, you don't really have to sit down and calculate this. If you just you go to Google and just put 100 binary to decimal, it'll tell you the number 4. So you don't really need to do that calculation yourself. Okay, so with this, let's just get started with combinational logic circuits.